Hi students, today we have to discuss the magnetic field due to a current carrying conductor. Okay, we want to study more about the current carrying conductor. It produces a magnetic field. An electric current through a metallic straight conductor produces a magnetic field around it. We can find it by using compass needle. Then, if we change the direction of current through the conductor, then what happens to the magnetic field? It is the positive direction, positive and negative terminal. Then the current is passed through this direction, is downward, and there is a magnetic field is produced. But if you reverse the current, if you reverse the polarity of the battery, then the current, the direction of the current is also changes. Direction of current changes in the opposite direction. Then the direction of compass needle also changes. If you place the compass needle here, then the direction is in the opposite to that of the first. Okay, you can find that the deflection of the compass needle is get opposite when we reverse the polarity, when we reverse the direction of the current. Okay, so when the direction of current changes, the direction of magnetic needle also changes. Then when the current increases, I increases, number of batteries increases, then what happens? The speed of the compass needle also increases. Deflection speed is increases. Okay, deflection of compass needle also increases. Deflection increases. Then, when the distance between the conductor and compass needle increases, what happens? Firstly, you place the compass needle here. Then, secondly, you place the compass needle here. Then what happens? What happens? When the distance between the conductor and the compass needle increases, the deflection is decreased. Okay, when distance increases, deflection decreased. These are the experimental results produced by a current carrying conductor. Then right hand thumb rule. Right hand thumb rule helps to give the direction of magnetic field produced by a current carrying conductor. Okay, this direction is inward direction and this represents outward direction. Okay, this cross means the magnetic field direction is inward to the board. This direction indicates the direction of the magnetic field is outward to the board because it is a three-dimensional picture. It's a straight conductor. Okay, straight conductor. So the magnetic field surround this field and this wire. So we can mark the direction here and here. This is inward and this is outward. What is the right hand thumb rule? It is Fleming's right hand thumb rule. It is explained by Fleming. Okay. Imagine that you are holding a current carrying conductor. It's a current carrying conductor. Assume that. Okay. It's a current carrying conductor. You are holding this current carrying conductor by your right hand. Okay. Imagine that you are holding a current carrying straight conductor in your right hand such that the thumb points towards the direction of the current. The thumb points towards the direction of the current. Here in this figure, this is the straight line, this is the conductor, and the direction of current is upward. So I hold this current carrying conductor with my right hand by pointing thumb towards the direction of the current. Okay, then your fingers will wrap around the wrap around the direction of the magnetic field lines. This figures gives the direction of the magnetic field lines. Okay, in the direction of the field lines of the magnetic field. This is known as Fleming's right hand rule. What it gives for a current carrying conductor, if the current direction is upward, then the fingers represents the magnetic field lines. If the current direction is outward, then magnetic field direction is in this way. Okay. Listen, it's a current carrying conductor, and use your thumb and hold your fingers, then it is wrap around in this direction. Wrap around in this direction. My fingers direction. Okay, it's my fingers direction. Three-dimensionally, this part. So the direction is like this, inward to the border. Here, the direction is into this figure, into the board, and here it is outward. Here it is outward, three-dimensionally outward. This point indicates outward, direction is outward. And this cross symbol represents inward to the board. The direction of the magnetic field line is inward to the board. It is outward. Okay. Then magnetic field produced by a circular loop. What is a circular loop? This is a circular loop. Okay. Then when a current flowing through a circular loop, it produces a magnetic field around the loop. The field lines at every point of current carrying loop can be represented as concentric circles representing the magnetic field around it. It would be larger and larger as we move away from the wire. Simply listen here. This is a circular loop, and the magnetic field is produced around this loop. Okay, magnetic field lines produced around this loop. Then what happens when we move away from this away from this loop at this position? What happens? The magnetic field direction is like this. The radius of the circle increases. Okay, the field lines every point of current carrying loop can be represented as concentric circles representing the magnetic field lines around it. It would be larger and larger circles away from the wire. When we move away from the wire, it is a larger circle. Okay, the radius is increases, something like that. These are concentric circles produced by a circular loop. At the center portion, you can find that this is the direction. In this way, this is the direction of magnetic field lines. These are magnetic field lines. What is the direction of the magnetic field lines on the center of the circular loop carrying a current? At the center portion, what happens? At the center portion, all passes in this way. So at the center portion, the direction is outward. At the center direction is like a straight line passing to the center point. In this direction, in this point, in the center point, all circles are meet at that point. Then it appears as a straight line. At the center, the direction is like a straight line passing through the center point. Okay. What are the factors affect on the strength of the magnetic field due to a circular coil of wire? It's a circular wire. What are the factors affecting the magnetic field produced by this circular loop? Okay, it depends on the following factors. First one, it inversely proportional to the radius of the coil, that is B is directly proportional to 1 by R. B means the strength of the magnetic field is inversely proportional to radius. When radius increases, B decreases. Okay. Then when the number of turns increases, that means N of the coil increases, the field strength also increases. If number of turns increases, I just add up one more turn and one more term. So if the number of turns increases, the magnetic field produced by this loop increases. Next one, the strength of the field increases when current passing through the coil increases. When I increases, B also increases. Okay, first point, radius increases, radius increases, B decreases. Second point, number of turns increases, B also increases. Okay, first point, when radius increases, B decreases. Second point, number of turns increases, B increases. I increases, B increases. These two are direct relation, and radius is inverse relation to the magnetic field. Okay, next one is magnetic field due to a solenoid. First question, what is solenoid? What is a solenoid? A coil of many circular turns, insulated copper wire wrapped closely in the shape of a cylinder is called a solenoid. Just listen here, is a copper wire, insulated copper wire. I wrapped this coil like a cylinder. This is solenoid. Okay. Coil of many circular turns, turns of insulated copper wire wrapped closely of the shape of cylinder is called a solenoid. So this cylindrical turns is known as solenoid. Then a solenoid is similar to bar magnet. When we provide electric current, then it acts as a bar magnet. One end of the solenoid behaves as a magnetic north pole, and while the other behaves like a south pole. Is similar to a bar magnet, and this is south pole, and this is north pole. It acts as a magnet. A magnet consists of south and north pole. Okay, the field inside are straight lines. The field inside are straight lines. Okay, the field is straight line. The direction is just opposite, north to south. So inside this, south to north. Inside the bar magnet, the direction of magnetic field is like a straight line. This indicates that magnetic field is the same at all points inside a solenoid. This is an important point. Inside the solenoid, the direction is always in a single direction. Okay, the field is uniform inside the solenoid. So one-word question: what is the direction of a magnetic field inside a solenoid? Is a uniform magnetic field in the same direction. Okay, in a single direction. The next one, what is an electromagnet? If you place a iron or steel inside the solenoid, then it is converted into an electromagnet. By introducing a soft iron or steel inside the solenoid, it magnetized, and this type of magnet is called electromagnet. So if you put a iron nail or soft iron inside this solenoid, then it acts as a magnet. It provides a battery. It needs battery electric current. So it is known as electromagnet.